Welcome back. In this segment, we're going to look at several concrete examples of using the product rule. So let's say you are shopping for a round-trip plane ticket between Chicago and Paris. So you want to count the number of different round-trip itineraries that you have to choose from. So when you look up the flights from Chicago O'Hare to Paris Charles de Gaulle Airport, you see 7 options. And then for the return flight from Charles de Gaulle to O'Hare, you see 5 options. So the total number of round-trip itineraries between Chicago and Paris is just the product of these two numbers, 7 times 5 or 35. And the reason we can apply the product rule here is because once you've made a choice for the first step, which is the trip from Chicago to Paris, you still have all of the choices available for the second step, which is the return flight. In other words, these two choices or these two steps in the task are completely independent. So that's an example of the product rule in action. For a second example, let's count the total number of bit strings of length 9. So to apply the product rule, you must frame the problem as a task that you can decompose into steps. So here we're trying to count the number of 9-bit strings. So one way to look at it is to convert this task into the task of choosing a random 9-bit string out of all the possible strings. So if you were to choose a random 9-bit string, you would start with 9 empty slots. And then you could break down this task into picking a bit for the first position and then picking a bit for the second position and so on all the way to the 9th position. So you can break down this task into 9 steps. So for the first step, how many options do we have for choosing the first bit? Well, we only have 2 possibilities, so we have 2 choices at that step. Now, how about the second step? Well, we also have 2 bits to choose from, so we have 2 choices. And similarly, of course, for every position in the bit string. Now, the key thing to realize is that the choice of a bit in this position is completely independent from the choice of a bit at this position and every other position. What that means is the choice you made here does not affect any of the other choices. You can still choose among the same options every time. So as a result, we have broken down this task into 9 steps. Each step has 2 ways of being completed. So we can just apply the product rule and multiply all of these numbers to get, as a final answer, 2 to the power 9. So of course you already knew that there are 2 to the power 9 9-bit strings. These are all the possible distinct patterns of 9 bits. But here is a different way of computing it using the product rule. For a third example, let's say you have a set of cardinality 9 and you want to count the total number of subsets of that set S. So S could be any set. Let's consider one in particular, say the set A, B, C, D, E, F, G, H, I. And now the question is, how can we convert this problem to a product rule type of problem? Well, again, the idea of counting the total number of subsets of S is equivalent to counting the number of ways that you can pick a random subset of S. So once you have the task of picking a random subset of S, can we break down this task into several steps? And the answer is, how would you go ahead and pick or build a subset of S? Well, one possible way is to go through the elements of S from left to right, and then for each element, make a decision, yes or no, whether this element belongs to the subset that you're building. So starting from the element A, we can decide yes or no, we want to include A in a subset. So we have two choices for this element. And then, of course, independent of that first choice, we also have two choices for B, whether we want to include B in a subset or not. And so on and so forth for each element in the set S. So how many ways do we have to pick a random subset from S? Well, because all of these choices for all of the elements are independent, we can just multiply those number of choices and get the final answer 2 to the power 9. Now, of course, you already knew this was the size of the power set of S, but here is one way to compute it using the product rule. Now, one thing you should realize is that it's not a coincidence that the size of the power set of S is equal to the number of 9-bit strings. In fact, these two problems are equivalent. So let me tell you what I mean. One way to represent a subset of S is to use a bit string with 9 bits where every bit position corresponds to one element in the subset. So this is element A, this is element B, all the way up to element I. And then these choices that we made, whether to include or not include the elements, can be recorded as a 0 or a 1. 0 meaning we don't include the element, and 1 meaning we do include it. So let's say we don't include any of the elements from A through I. Then you get the bit string with all zeros. This represents the empty set, which is a subset of S. Now, on the other hand, if we were to take all of the elements of S, then the subset we get is S itself, and it's represented by this bit string. And as a last example, let's say I want to take the subset containing only the elements A and D. Then I represent that subset with this bit string. So in conclusion, there's a one-to-one correspondence between the subsets of S and the bit strings of length 9, because S contains 9 elements. So it's not a coincidence at all that we get the same number here and there. For our next example, let's say we still have a set S with cardinality 9, and we want to count the total number of pairs of elements of S. Remember that a pair is a tuple with 2 elements. So the task here is to count the number of such pairs, which is equivalent to counting the number of ways that exist to pick a random such pair. So how can we decompose this task? Well, to pick or build a random pair, we can first pick the first element of the pair, and we have 9 choices for this first step. And then the second step is to pick a second element for the tuple, and again we have 9 choices. So according to the product rule, we have 9 times 9, or 81 pairs of elements of S. Now let's look at a slightly different example. We still have a set S with cardinality 9, but now we're counting the total number of pairs of distinct elements, which means the first element of the pair must be different from the second element. So how many ways do we have to build such a pair? Well, for the first element of the pair, we still have 9 choices. But once we made a choice for the first element, we only have 8 choices remaining for the second element, since we're not allowed to choose the same element as we chose in the first step. Now, these 9 and 8 choices are independent, so we can multiply them together, and the final answer then is we have 72 pairs of distinct elements of S. So our next exercise is to count the number of ways to shuffle the letters in math. In other words, we want to count the number of permutations of the letters. So remember, the usual trick is to convert the counting task into a task of building or selecting a random permutation out of the set of all possible permutations that we're trying to count. So the total number of ways of building this random permutation is going to be equal to the total number of permutations. So now let's break down this task of building a random permutation. Well, we're going to end up with a 4-letter sequence, and now it's pretty obvious how to break it down. We can break it down into 4 steps. The first step will be to pick which letter is going to go into the first position. And we have 4 choices for this step. For the second position, we only have 3 choices left, because once we have chosen a letter for the first position, it can't go in the second position. Now, similarly, for the third position, we only have 2 letters left to choose from, so we have 2 choices here. And for the last position, we don't have any alternatives. In other words, we have only 1 choice, the 4th letter that is left over after you've completed the first 3 steps. So now we can apply the product rule and multiply all of these numbers to get 4 factorial. And this is an informal proof of the fact that the total number of ways to shuffle n letters is always equal to n factorial. For a 7th example, let's get the number of subset of size 2, where the universe, as before, is a set S of size 9. You can think of this set as an example here. So again, the counting job is going to be converted to a task of picking or building a random subset of size 2 from a set of size 9. So here is a skeleton for such a subset. And now we can decompose this task of building a random subset into 2 obvious steps. First is choose the first element of the subset. Of course, we have 9 choices for this step. And then the second and last step is to choose a second element of the subset. Now, how many choices do we have for that? Well, we can't choose the same element we already picked in the first step because we can't have the same element twice in a set, so we only have 8 choices left. And therefore, according to the product rule, the total number of subset of size 2 is 72. Now, this is a little bit strange because if you look at problem 5, we had the total number of distinct elements or pairs of distinct elements was equal to 72 as well. That's a little bit strange again because a pair is not the same as a set. Remember, the main difference is that in a set, the order doesn't matter, whereas in a pair or in a tuple, it does. So there's something wrong here. They can't be the same number of pairs as the number of subsets. And of course, the reason is that this answer is incorrect. So I want you to pause the video and make sure you figure out why this answer is incorrect. Okay, so let's take an example to make sure you understand this. Let's say here I pick A and then here I pick B as the 2 elements of S to make up the subset. So I have the subset A comma B. Well, what if I had picked the letter B for the first choice and then the letter A for the second choice? I would have gotten the set B comma A, which of course is exactly the same set as A comma B. So what happens here is we're counting every set twice, or every subset twice. So this number is too large, in fact, is twice the actual number, and the real answer is 72 divided by 2, or 36. For our 8th example, I want you to count the number of ways to shuffle the letters in comp sci. So please pause the video and come back when you have an answer to check against mine. Okay, so hopefully you realize that this problem is very similar to problem 6 when we're counting the total number of permutations of the letters in this word. So I'm going to follow the same approach. I'm going to decompose the task of building a random permutation into 7 steps Here are the numbers of options for all of the steps. Multiply them all together to get 7 factorial. So, are you happy with that answer? I hope not, because this is not a correct answer. So if this is the answer that you got, make sure you stop the video again and try to figure out why it's wrong. Well, remember in example 6, I said the total number of permutations of n letters is n factorial. Actually, the real rule is of n distinct letters. But here we have the letter C occurring twice in the string. So what happens? Well, what happens is, if you look at all the permutations we computed here, there are always a pair of permutations that are identical except for the permutation of the two C's. But because the two C's look the same, these two permutations are actually the same. In other words, we're counting every permutation twice in this number, so the correct answer is 7 factorial divided by 2. So make sure you're comfortable with this reasoning, and after that, try to solve similar problems where you can pick your own strings with repeated letters. And as another example for you to work on at home, why don't you count the number of subsets of size 7, again when the universe is a set of size 9. And I encourage you to solve this problem in a couple of different ways to make sure you get the same answer.